In this lecture, we're going to be covering the max and min of a multivariable function. And specifically, we're going to talk about local extrema first, and then we'll eventually get to the absolute extrema. So we'll begin by defining what it means to be a local max and local min in the context of a multivariable function. Now, thankfully, it's very similar to a single variable function. We just have to deal with one extra variable, right? So just by starting off with a definition, a function f of xy has a local max at some point a, b, if you pick any essentially z value, which is like our y value, f of xy is less than that point that you pick, essentially, right, at the z value. So, and then for any point nearby. Not that that's really important to us, but it is part of the definition. So effectively, if you think about it three-dimensionally, it's just saying it's the tallest point. It's like the mountain of the function. And then a local minimum is just reversing that. So a function f of x comma y has a local min at some point a comma b if f of x comma y is greater than that point that you pick for really any value in the proximity. Now, what's interesting about three dimensions is there is a third scenario, which we're going to call the saddle point. That's a scenario where it is a point of extrema. In one direction, it's the minimum, and in the other direction, it's the maximum. And it kind of looks like a saddle. So, but we'll talk more about that once we start getting into the actual derivative test. So just to kind of illustrate this, right? If you talk about a single value function, that's your max and that's your min. Now we're saying, okay, if we draw a three-dimensional shape like this, well, this could be the max. That's like the tallest point. And then this down here could be the min, right? And now we're just kind of thinking about it in one more dimension, right? So now it's z equal to f of x comma y. Now, luckily, the procedure in finding the max and min is very similar to single variable in that you will have to find a critical point. You will have to set a derivative equal to 0, and then you'll basically have to use some kind of test to find the max and min. And in multivariable, we skip straight to the second derivative test. So whereas in single variable, we have the first and second derivative test. So fundamentally, they're the same concept. The only issue is multivariable has twice as many variables. So it's just more algebra in the long run. So now we're going to define what is most important thing here, and that's the critical point, because that's how you're going to find your max and your mins. So what is a critical point? A critical point. So a point A comma B is a critical point. And another word that people often use is stationary point. If the first derivative, sorry, not the first derivative, the partial derivative with respect to x of your point AB is equal to 0, and the partial derivative with respect to y of your point AB is also equal to 0. Now, it is possible to have a critical point if one of these partial derivatives is undefined. In this class, we're really not going to focus on that case, but that is also another option. So let's do an example of finding the critical point. So find the critical point of f of x comma y equal to x squared plus y squared. So the first thing that you want to do in finding the critical point is just take the partial derivative. So fx and fy. There's not really a formula here. So we just take the partial derivatives. So fx, looking at our function, is going to be 2x, and then y squared has no x term, so it's still 0. And then fy is going to be x squared has no y, so it becomes 0, and then y squared becomes 2y. So we have our partial derivatives. Step 2 is set both equal to 0. So fx equals 0, fy equals 0. So 2x equals 0. So x is equal to 0. And then 2y equal to 0, y is equal to 0. Now, this is one of those things where you kind of have to be careful. Technically speaking, x equals 0 just means x equals 0. That doesn't mean the y value that you also found is connected to that 0. They may actually not be. But sometimes there is no other option. So at this point, you would actually use your equations to find the other variable. So then step 3, okay, is going to be to find coordinates. Now, what's kind of interesting about this problem specifically is that essentially, because of the equation itself, you're basically going to get 0, 0, just because when you try plugging it into the other equation, you just get 0. So, but from that, we will get that. So note that fx is equal to 2x and fy is equal to 2y. So if x is equal to 0, then y has to be equal to 0 for both equations to be true. So we get 0, 0. And then if you make the same argument, which is if y is equal to 0, then x has to be 0 for both equations to be true. And in this example, that's kind of the most confusing part because there is no other variable to plug it into. So this is one of those where observation is actually how you get the critical point. So there it is. Now, you could always plug back in your value just to make sure it works, because again, the key to being a critical point is both equations have to be equal to 0 when you plug in x and y. So if you plug in right here 0, you get 0. And if you plug in 0 here, you get 0, right? So that's our ordered pair. Now, in the next example, it will be a lot more clear that the x and y value may not go together, and in fact, they don't go together, right? So that's just the nature of this example specifically, is the critical point just ends up being 0, 0. And that's always a recommendation that I make to any student. Always check 0, 0 first, because 70% of the time it is a critical point. So, and it's very easy to check. You just plug in 0 into everything, and if you get 0, you get 0. If you don't, then you can eliminate one option. So highly recommend you always check 0, 0. So now let's find critical point of f of x equal to, sorry, f of x y equal to x squared y minus x squared minus y squared. So step 1, find fx and fy. So the partial derivative with respect to x is going to be, well, I have x squared times y, so that's going to be 2x times y because the y is treated as a constant. Minus x squared becomes minus 2x, and then minus y squared becomes 0 because it's just a y term. And then fy, we're going to get x squared because the y becomes 1, minus 0 because x squared has no y term, and then minus 2y. And often you'll see with a lot of these problems is there's some kind of like symmetry. That's just how they usually pick out the problems. Step 2, you're going to set each of the partial derivatives equal to 0. So we get fx equal to 0, which means 2x y minus 2x equals 0. Fy equals 0, so x squared minus 2y equals 0. And then from there, you're just gonna see if you can, simplify anything, right? And also, like I said, it's always good to check if 0 is an answer, right? So if I plug in 0, 0, right? So checking, sorry, we'll make that step 3. Check for 0, 0. And so 2 times 0 times 0 minus 2 times 0 equals 0. And then 0 squared minus 2 times 0 equals 0. 0 equals 0. 0 equals 0. So 0, 0 is an answer. And you just got a solution by checking the values. Now, step 4 is going to be solve equations. So you set them equal to 0, and then you check for 0, 0, and now we're going to solve them, right? So the question that I get is, how do I know which equation to start with? Experience more than anything will kind of lead you in the right direction. But the rule of thumb is first, check to see if there's any equations with one variable, because sometimes there will be. And I look and there is no equation with a single variable. So I say, okay, that's not a good option. Then to me, I look for any equations that look like they kind of have some cancellation maybe, or they don't have high degrees, like they're all degree 1. So the first equation, fx, that has degree 1. So we'll call this equation number 1, and we'll call this equation number 2. So from there, we're going to solve equation number 1, which is 2xy minus 2x equals 0. And some strategies that you'll kind of have to be able to do is, usually you'll have to be able to factor out something. So we see that we can factor out an x from both of them. So x and then 2y minus 2, like that. And now that we have it as a multiplication, we can use the 0 product rule, what you would say, and basically set each of these equal to 0. 2y minus 2. And so then if I solve for y, so 2y equals 2, y is equal to 1. So essentially, now I have some choices, right? Now here's the thing, and I mentioned this in the last one. These are not necessarily going to go together. So these are actually not related. Okay? It's not 0, 1 is an answer. You could try it, and maybe it is an answer. All this tells you as the reader is one of these works for just that variable. So I have to use the other equation to figure out what the y value or x value is. So that's what we're going to do next. Okay, we're going to, use equation number 2 to find missing variable. And so because this is only ever 2 partial derivatives, you're going to use one equation to solve x and y, and then maybe the other equation to solve for the missing variable. Now, sometimes you will get equations where you can solve them at the same time using, linear systems, but these are nonlinear problems. So equation number 2 says, so we're going to plug in x equals 0 into equation number 2. So equation number 2 is 0. Let's write down the equation number 2 first. X squared minus 2y equals 0. And then I'm going to replace that with 0, like that. And then I get negative 2y equals 0. So y is equal to 0 because I divided out the 2. And what that tells us is that when x equals 0, y is equal to 0. So 0, 0 is a solution. And now you might be wondering, hold on, we just got that earlier. Well, this is just reinforcing that our answer was correct, right? Like I said, 0, 0 is such a common answer with these that you can just always check it before you do anything and you at least get one answer out of it, right? So we did that. Okay, now we're going to plug in y equals 1 into 2. So x squared minus 2y equals 0. X squared minus 2 times 1 equals 0. X squared minus 2 equals 0. You could quadratic formula, you could factor this, or you could use the, if I move the 2 over, take the square root of both sides, I get x equals plus or minus the square root of 2. And so this just tells me when y is equal to 1, my x value is either square root 2 or negative square root 2, 1. But they both have the same y value of 1. And so these are my critical points. So I have 0, 0, and then square root right there. And that's how you find the critical points. And essentially, for this section, extreme value theorem, and for the optimization problem, there will be critical points that need to be found. So getting comfortable finding critical points is key to the last 3 sections of this chapter. So now that we can find critical points, we're going to be able to now use those to figure out whether they are a max or a minimum. And the way we do that is through the second derivative test. So the second derivative test, it's just going to have to be a formula you memorize, right? So you really just got to focus on memorizing this formula. Second derivative test. So suppose AB is a critical point. We can test for local extrema by computing the following. So the formula for the second derivative test will say that D, and we'll explain what the letter D stands for, is equal to the partial derivative, the second partial derivative of your critical point times the second partial derivative with respect to y of your critical point minus the partial derivative with respect to x and y of your critical point, and then that's all squared. Now, to be clear, because in this formula it looks kind of confusing, you're evaluating at AB, you're not multiplying by AB. That's just a function notation. But because of all the letters, it can often be misread. So just to be clear, you're evaluating A comma B in the second derivatives. So if you want to shorthand this, it would be fxx, fyy minus fxy squared, right? So like that's the shorthand notation. Now the D stands for discriminant. The D stands for discriminant. It's just a formulation to calculate a value. So in this case, we're going to have 3 different cases. Technically 4, but really we're going to be looking at 3. So if your value of D, or the discriminant, is positive, and your fxx, which is the second derivative with respect to x, is also positive, so double positive, it's a local min. if your discriminant is positive and your second derivative with respect to x is negative, so less than 0, local max. If your discriminant is negative, so if you calculate the discriminant and it's negative, you don't even care what the other values are. It's just automatically a saddle point. And then if D is equal to 0, we would say inconclusive. But we're not going to deal with that case in this class. The technique after that point would be to kind of look at points around the critical point and figuring out what the general behavior is. And so going to saddle point, this just means max in one direction, minimum in other direction. So if you picture a saddle, you know, in one direction it's going up, and in another direction it's going down. So in this case it's going like this, and then in this case it's going like that. Not a very good saddle to be drawn, honestly, but that's kind of the basic principle. So how do we use this to calculate the local extrema? Well, luckily for us, it's not too bad. Find local extrema, or max and min, for f of x comma y equal to x squared plus 2xy plus 2y squared minus 8x plus 6y. Now, you would think, wow, that's a very long equation. That's probably going to be challenging. What's actually interesting about this is it's not how long the equation is that makes these challenging, it's the degrees. So this equation would probably be a lot easier than if it were just like 3 terms and one of them was x cubed. Because the higher the degree gets, the worse the algebra becomes. It's the degree that makes these difficult, not how many terms you have. So if you see like degree 3 and 4, that's going to be a lot worse than like 8 terms, because eventually with 8 terms, a lot of it just cancels out or it combines into smaller things. So it's really the degree that's the most challenging part. So step 1, formula, right? So we just got to write down this formula so that we memorize it. Like that. And then after that, we're going to do our partial derivatives. So you can take these all at once, but we should really just do the first derivatives. And we're going to set them equal to 0. So we're going to combine that step. So fx equal to 0 and fy equals to 0. So the partial derivative with respect to x, actually, you know what? Let's just keep it simple and just do the partial derivatives first. Like that. So fx is equal to x squared becomes 2x. 2xy, so has both x and y. So that means the y stays because it's a constant, but the x goes away. 2y squared has no x, so it's 0. Minus 8x becomes a minus 8, and then 6y becomes 0. And then fy, well, the first one doesn't even have a y, so it's 0. 2xy becomes 2y, and then 2y squared becomes, whoops, common mistake that is made here. The derivative of 2xy would have been 2y, and the derivative of 2xy with respect to y should be 2x. That's kind of a thing that happens is when you are doing a partial derivative, if you're doing one with respect to x, because in your brain you're thinking x derivative, you will sometimes just write down x on accident when you really meant to write the other letter, as I just did right there, right? So the derivative of 2xy with respect to x is 2y because the y is a constant. And I even said that out loud, but I still wrote down x because I thought x derivative. So got to be careful with that. 2y squared becomes 4y, minus 8x becomes 0, and then plus 6. okay? Now, if you get an equation that looks like that, you should be very happy, just because that's going to be a nice linear system, right? So that's really, really what you want. So from there, we're going to set these equal to 0. So 0 equals 2y. Now that was 2x. So I was completely wrong. It was 2x just because it was x squared. So again, one of the things about partial derivatives is you start looking at all these letters and they all look the same to you. So no, it was 2x. I take everything back I said. I was looking at 2xy, but I forgot there was an x squared in front of it. So you just got to be careful with all of these letters. Very easy to make mistakes, as we did right there. So then we just write down everything we see. Like that. And so we set these equal to 0. Now, whenever you have something that looks like this, it's not a bad idea to, think of strategies that we've learned. So if we think back to the very beginning of this class, we learned how to solve linear systems, right? And so this is really just a linear systems problem. So you can use elimination method, you can use substitution method. So in this case, I am going to use elimination method. So we're going to solve for x and y. So what I'm going to do is I'm going to move the 8 over. So I'm going to move that over here, and I'm going to move this over here. So what I end up getting is 2x plus 2y equals 8. And then 2x plus 4y is equal to -6. So I added the 8 over to the left side, and I subtracted the 6 over to the left side as well. And then I just flip the equations because that looks nicer for me. You don't have to do that step. That's just something you can do with the equations. You can flip them on the equal sign. And so what I'm going to do now is I'm going to multiply this by -1, this by -1, and I'm going to add them together. Okay. Actually, let's just show the modification. So this now becomes -2x minus 2y equals -8. 2x plus 4y equals -6. So now we add together and we get cancellation. 2y equals -14. And so if we divide the positive 2 over, we get y equals -7. So we got a point. Now, I am going to use this point to plug it into one of the equations and then solve for x. So subbing y equals -7 into either equation. So it doesn't matter which one you pick, just pick either, equation 1 or equation 2. So we're going to do y equals -7 into equation number 1. So 2x plus 2 times -7 minus 8 is equal to 0. And then if we simplify that, and actually, let's just move this over here so we're not too cramped. And so we get 0 equals 2x minus 14 minus 8. 0 equals 2x minus 22. 2x equals 22. Divide the 2 over. X is equal to 11. So we get 11. So now we have our ordered pair. So we have 11 comma -7. And make sure you put the, remind you, x comma y. Always put the x first and the y is second. I've seen many, many students, because the first thing that they solve for was the y term, they think that's the x term for a brief moment. And you just want to avoid that. So most of the work is that. Most of the work is just finding the critical point. Now we just need to plug into the formula. That's step 5. Step 5 is to plug in. Well, before we do that, we got to take our partial derivative. So find fxx, fyy, fxy. So we got to find the second partial derivatives. Can't forget about that. So just to remind you, fx was equal to 2x plus 2y minus 8. And so fxx, so you just do the partial derivative again with respect to x. And sometimes you will just get numbers, right? In this case, we just get 2, 0, 0. Okay, so there it is. And then if we do fy, which was equal to 2x plus 4y minus 6, fy is also equal to 4. And we just get a number, 4. And then fxy is equal to, so you take the first partial derivative with respect to x, and then that's going to become 2. Because 2x becomes 0, 2y becomes 2, and minus 8 becomes 0. So we have that. And then so d is equal to fxx, fyy, minus fxy at 11, not 11, yep, no 11, negative 7, right? Should make sure that was a great point, yep. So you're going to plug in 11, negative 7 into all of the second derivatives. But notice the second derivatives are all numbers, so there's nothing to plug in. So then now you just substitute. So 2 times 4 times, not times, minus 2 squared. And so we get 8 minus 4, and we get 4. So d is greater than 4, which means d is equal to 4, which is greater than 0. So then fxx is equal to 2, which is greater than 0. So because you have this case, you have a local min, like that. Local min. And that's all you have to do. So for the next example, we're just going to find the local extrema. And for this one, the critical points are going to be a little bit more challenging to deal with, but also we're going to have more than one critical point here. So for this example, find the critical points and local extrema for f of x comma y equal to x cubed minus 9xy plus y cubed. So at first glance, you would think, oh, this one looks a lot nicer than the previous one. And the reality is that is not true because degree 3 is much worse than degree 2. So we're going to have to deal with that. So step 1 is going to be formula. So we just need to remind ourselves of the formula, which is this. And so from there, we are going to now just take the first partial derivative. So taking fx and fy. So fx, okay, x cubed becomes 3x squared minus 9xy, hopefully correctly this time, becomes 9y minus, because x becomes 1, and then y cubed becomes 0. So fy, x cubed becomes 0 this time, minus 9xy becomes minus 9x because of the fact that the y becomes 1, and then the y cubed becomes 3y squared, just like that. And so from there, we're going to set this equal to 0. So step 3, set each of these equal to 0. 0 equals 3x squared minus 9y. Also, there's nothing stopping you from putting the 0 on the right side by default. It's just when I learned it, to me, that's the most natural way. But sometimes I do like putting it on the right side if it just looks nicer in my brain. So again, personal preference. And so yeah, we have these equations. We're going to want to isolate something at some point. So that's going to be step 4. So step 4 is to solve equations. To solve equations. So like I said, you always want to ask yourself, okay, are there any equations with a single variable? Okay, no. Are there any equations with degree 1, like no squares or anything like that? No, that's another no again. So then now I gotta think, okay, I don't have either of those scenarios, which means I'm gonna probably have to do substitution. So when you start running out of things to do that are, simple and quick, it starts to become evident that substitution will be the route that you have to take, which means you're going to have to figure out, okay, which variable would be a good substitution, right? Like that's what you're thinking. Or is there a way to make this equation look nicer, right? Like you don't want to do division, like you want to avoid division if you can. So I think to myself, okay, just looking at the first equation, 3x squared minus 9y, right? And again, this is a scenario where it doesn't matter where you put the 0. I say to myself, you know what? I'm just going to move one of the variables over. So I'm going to add the 9y over. And I get 9y equals 3x squared. And then I notice, hey, I can divide both sides by 3. That looks nice. And so I get x squared equal to 3y, right? And just for the sake of it, I'm going to flip it because you're allowed to do that. So x squared is equal to 3y. Okay, that doesn't look that bad. Looks kind of nice compared to what I used to have. So let's just say equation 1. We're going to call that equation 1. I haven't solved for anything yet, but I'm just thinking to myself, okay, maybe I can do something with that. And then you take the other equation. And then you kind of do the same thing. You know what? I'm going to add the 9x over, right? I can do that. And so I get 9x equals 3y squared. Divide both sides by 3. And then I kind of end up getting the same thing, right? But again, I say to myself, you know what? I'm going to flip it because I just want it to look a little bit nicer. So y squared equals 3x. And there are my equations. And so you look at these together and you say, is there anything that I could do where I could maybe substitute one of them into the other? And then you keep looking and you keep looking and you realize, you know what? What if I took this y value right here? You took this y value and you got it by itself and then you plugged it into here, right? That's an option. Or maybe you're thinking to yourself, you know what? I could also take this x value, I could isolate it, right? Divide the 3 over, and I could plug it into this x squared. Now, what sounds better? Plugging in something into a square or, or I guess the better question is, which sounds better, plugging into an x squared or a y squared, right? Which letter do you like more at this point? Most people like the letter x more to work with. So, but in either case, you're going to have to do the same thing. So they're both the same, but sometimes maybe one's a little bit better than the other. It just depends. So for me, I'm going to basically solve for y, just because to me that just feels the most natural. So taking equation 1 and isolating y, so x squared equals 3y, y is equal to x cubed. Nope, that's incorrect. X squared divided by 3. I just divided both sides by 3. And so now I'm going to call this right here equation number 3. And what I'm going to do now is I'm going to substitute that into equation number 2, right? So that's going to be what I do next. And let me see if I can give myself just a smidge more space here. So now sub in 3 into equation number 2. Once you use an equation for substitution or anything like that, then you can't use it again for substitution because you've already used it up. So got to go to the next equation. So I used 1 already, got to use 2. So y squared equals 3x. And then basically I'm going to take this, plug it into here, and then I get x squared over 3 squared equals 3x. And is this getting better? I mean, maybe. The good news is I have one variable now, right? So no matter how bad an equation looks, if it has one variable, you can solve for it. If it has more than one variable, then you probably can't solve for it. That's kind of the trade-off here. So then you're going to square the top and the bottom using the property of exponents, right? So a over b to the nth power is equal to a to the n over b to the n, right? That's a property of exponents. So this becomes x to the fourth power over 9 equals 3x, right? Again, just got to remember that exponent rule. And then from here, I'm just going to multiply both sides by 9, like that, and like that. And I get cancellation there. X to the fourth equals 27x. And then you might be thinking, man, this is getting a lot worse. Actually, it's getting a lot better because now what I can do is move the 27 over and get that. And then again, you might be thinking, well, x to the fourth degree, we don't ever really do those. Those aren't fun. But here's the best part. They both have an x term. So whenever everything has an x term, just factor as many as you can. So I can factor out one of them, which leaves me a third, sorry, cubed. And then the 27 loses its x term, so I get that. And then now that I have a multiplication of a variable times a variable, I can set them both equal to 0. And then you might be thinking, okay, I got x equals 0. That's cool. But what about this x cubed minus 27? We can use our little trick for this one. Just move the 27 over and then take the root of whatever the degree is, so the cube root, like that. Now, if you're thinking, is there a plus or minus? Because every time I take the square root, there's always a plus or minus. Here's the good thing, if you don't remember this. Whenever you take the cube root or the fifth root or an odd root, so 1, 3, 5, 7, 9, there is no plus or minus. The plus or minus only happens when you do an even root, 2, 4, 6, 8. So thankfully for us, there's only one of them, and it's that. So now I have two x values. So I'm going to use that to find the y values now. So that's going to be my next step. So now that I have my x values, okay, so find the y values of x equals 0 and x equals square root, correction, cube root of 27, which if you think about it, what is the cube root of 27? It's 3, because 3 times 3 times 3 is 27. So, and it doesn't matter which equation you pick. You can pick equation number 1, 2, or 3, but ideally, you would want to plug it into equation number 3, because that'll give you the y value directly, right? It's already in terms of y equals, but it doesn't matter which equation you pick. So we're going to sub in x equals 0 into equation number 3 from earlier, which said x squared over, to be correct, 3 equals y. So 0 squared over 3 equals y. So y is equal to 0, which means I get 0, 0. That's my first order pair. And you know what we should have done earlier? We should have checked 0, 0 as a potential solution, and we would have gotten that for free. And then now we're going to sub in x equals 3 into equation number 3. And so x squared over 3 equals y. And then I get 3 squared. Always put parentheses whenever you plug in a number into a variable, especially if it's negative, because that will make a difference in the answer. And then if you calculate this, you get 9 over 3. And so you get 3 equals y. So you get 3 comma 3. Is it a coincidence that they're both the same number, like 0, 0, 3, 3? Yeah. Well, I mean, probably not because of the type of function it is, but it's a coincidence in just the general nature of it. Okay. So we did that. So solve the equations. Now we just got to take our second partial derivatives. Like that. So fx was equal to 3x squared minus 9y. So then the second partial derivative is going to be 6x minus 9. And then Fy is equal to negative 9x plus 3y squared. So Fyy is equal to, well, correction. The derivative of minus 9y with respect to x is 0. Again, very easy to make mistakes. Even though I've been doing this for a long time, I still make partial derivative mistakes. So keep an eye out for those. So the derivative with respect to y of negative 9x is 0, and then this becomes a 6y. Okay. And again, there tends to be a lot of symmetry with these, and a lot of it has to do with the problems that they pick. If you just pick random equations, they wouldn't be that nice looking, but they kind of like to pick problems that have symmetry to it. And then fxy, so just pick whichever one you want and take the partial derivative with the opposite letter. So if I pick fxy, so this one right here, it's going to be negative 9. And if you did the other one, fyx, you would also get negative 9 because they should be equal to each other, right? And then so, sorry, step 6, plug into formula. So d is equal to fxx, fyy minus fxy at a comma b. So now you're going to have to do this for multiple coordinates. So for 0, 0, we're going to get d is equal to 6 times 0. I like to put square brackets to separate them. And then 6 times 0 for y minus negative 9 squared. And again, parentheses here are important, especially for that minus 9, right? So negative 9 squared is 81, but the minus on the outside makes it a negative 81. So d is negative, so less than 0, which means saddle immediately. I don't have to worry about fx. It's saddle because like that. There you go. And then you go to the next coordinate, 3, 3. So d is equal to 6 times 3, 6 times 3 minus 3 squared. And so I get 18 times 18, so 18 squared. And so 18 times 18 is 324 minus 9. And so 315, which is positive. And then that means I got to check fxx, which is equal to 6 times 3, which is equal to 18, which is positive. So because they're both positive, that means we have a local min. Right there and right there. And so that's how you do the extrema when you have more than one point. So you just have to be able to check them for each partial derivative. It is important that A, you don't use the wrong partial derivative. I've seen people use the first one. And B, if they're just numbers, then that's the number that you're going to use. So that does happen a lot of the time. So just make sure you don't plug in points where there is no variables. So now we're going to look at a word problem. So the cost of controlling emissions is given, C of xy equals 1,000 plus 800x squared plus 500y squared minus 400x minus 300y, where x is the reduction in sulfur emissions and y is the reduction in lead emissions by pounds, respectively. How many pounds of each emissions would yield the lowest cost, right? So one of the important things when you're doing any of these problems is recognize, is this a max or a min problem? And so in this case, they've said lowest cost, which means we're minimizing, right? And so just like any of the other problems, you're just going to follow the same progression. You're just at the very end going to state what these values actually mean. So from there, we would say, okay, step 1, what is the formula? So D is equal to fxx fyy minus fxy squared. And we don't need to put parentheses on that one. Step 2 is, okay, we're going to find the critical points, but before we do that, we're going to find the partial derivatives. But as you get more comfortable, you can kind of combine step like 2, 3, and 4 all together into one. but the partial derivatives are going to be, well, 1000 becomes 0, 800x squared becomes 1600x, 500y squared becomes 0, minus 400, and then 300y becomes 0. And then cy equals about the same, 1000y minus 300. And then we just set each of these equal to 0. And so from there, we get 0 equals 1600x minus 400. And then 0 equals 1, not 100y, 1000y. There we go. 1000y minus 300. Now, luckily with this one, there's only one variable for each equation. So step 4 is we're going to solve. So solving each one, you don't have to do substitution or elimination. You just get to solve each variable as a regular algebraic equation. So I added the 400 over, I divided by 1600. X is equal to 0.25 or a quarter. And then 0 equals 1000y minus 300. And so if we add the 300 over, we get 1000y. And so then if we divide the 1000 over, we get y equals 0.3, right? So that means a quarter pound of sulfur and a, 3/10 or 0.3 pounds of lead will result in the lowest cost, okay? That is our minimum cost. So ultimately, all of these problems are going to come down to taking the partial derivatives, setting them equal to 0, and then solving for the critical points. And what makes the problem challenging is really just finding the critical points. Usually, if it's like a word problem, they tend to be a lot simpler because the interpretation is more important. So again, for this one, the minimum cost, sorry, the pounds, or I guess we could say it this way, 0.25 pounds of sulfur and 0.3 pounds of lead emissions results in the lowest cost. So that's our interpretation. But other than that, you're just taking partial derivatives, setting equal to 0, solve critical points, plug into formula. Now, if you're wondering, well, what happened to the whole D equation? Why didn't we do that? Well, in this problem, we only had one critical point. And 90+% of the time, if you only have one critical point, it's going to be the extrema that you are looking for. So in this case, they said minimize, we had one. Now, if you end up doing a problem where you have more than one extrema and they do want you to find like the max or min, then you would have to use the formula to just verify which one is the max or min, right? But generally speaking, in these types of problems, if it's only one critical point, it usually is. It would be kind of like a trick question if it wasn't, because then you basically, there is no answer. There is no minimum or maximum value, especially because there's no boundary. That's where the extreme value theorem comes into play. And that's what we're going to talk about next.